We tend to think life has limits. Extreme pressure, total darkness, freezing cold should make survival impossible. But the deep sea, Earth's largest habitat, defies these assumptions. Over 80% of the ocean remains unmapped, yet creatures thrive where no life should exist. This video explores the astonishing adaptations that make the impossible possible. Take pressure. At 4,000 meters depth, it's 400 times atmospheric pressure, enough to crush most submarines. Yet fish like the Mariana snailfish live at 8,178 meters, deeper than any other vertebrate. How? Their bodies produce a molecule called TMAO that stabilizes proteins under crushing force. Then there's the darkness. Sunlight never reaches below 1,000 meters. Yet here, life doesn't just survive, it thrives. Hydrothermal vents discovered in 1977 belch superheated water rich in minerals. Tube worms grow over 2 meters tall with no mouth or gut, relying on symbiotic bacteria that convert chemicals into energy. This chemosynthesis powers entire ecosystems independent of the sun. At the surface, we live under 1 atmosphere of pressure, but descend just 4,000 meters into the ocean, and that pressure skyrockets to 400 atmospheres, enough to crush a military submarine like a tin can. So how does anything survive down there? The answer lies in molecular adaptation. The answer lies in the cells of deep-sea fish. They produce a molecule called trimethylamine N-oxide, or TMAO. This compound stabilizes their proteins, preventing them from being flattened and denatured under extreme pressure. Without TMAO, their bodies would literally collapse. But pressure isn't the only challenge. At these depths, sunlight never reaches, temperatures hover near freezing, and food is scarce. Yet life not only endures, it thrives. Creatures like the barrel-eye fish, with its transparent head, have evolved bizarre adaptations to navigate this alien world. So how do deep-sea fish survive pressures that would crush a submarine? The answer lies in a molecule called trimethylamine N-oxide, or TMAO. At depth, TMAO stabilizes proteins, preventing them from being flattened by the immense force. The deeper the fish lives, the more TMAO its cells contain. This chart shows the correlation between depth and TMAO concentration. Take the Mariana snailfish, filmed at over 8,000 meters in 2023. Its body contains record levels of TMAO, allowing it to thrive where pressure is more than 800 times atmospheric. Without this molecular adaptation, its proteins would unfold, and its cells would collapse. TMAO isn't the only trick. Some deep-sea fish have flexible bones and porous skeletons to avoid being crushed. Others produce antifreeze proteins to keep their blood flowing in near-freezing waters. Each adaptation is a precise solution to an extreme problem. But here's the real puzzle. Sunlight never reaches these depths. So what powers this ecosystem? In 1977, scientists diving on the Galapagos Rift found the answer: hydrothermal vents spewing mineral-rich water at 400 degrees Celsius, creating oases of life in the abyss. At these vents, bacteria convert hydrogen sulfide into organic matter through chemosynthesis. Giant tube worms, growing over 2 meters tall, have no mouth or gut. Instead, they house these bacteria inside their bodies, forming a partnership that defies everything we thought life needed. This discovery shattered the long-held belief that all life depends on sunlight. Chemosynthesis powers entire communities, from vent crabs to yeti crabs, proving that life can thrive in total darkness, sustained only by Earth's internal heat and chemistry. So darkness is not a limitation. It's an opportunity. How? Over 75% of deep-sea creatures produce their own light through bioluminescence. This is no mere glow. It's a sophisticated tool for communication, camouflage, and hunting. Take the anglerfish, whose glowing lure attracts prey in the abyss, or the atolla jellyfish, which emits a spinning burglar alarm to summon larger predators when attacked. These aren't passive glows, they're active strategies honed by evolution. This mastery of light turns the deep sea into a realm of silent communication and deception. As marine biologist Dr. Edith Witter puts it, it's a world of perpetual darkness, yet life finds a way to glow, to hunt, to survive. Bioluminescence is the key to thriving, where no sunlight penetrates. So if pressure and darkness can be overcome, what about size? For centuries, sailors told tales of a monster with eyes the size of dinner plates and tentacles that could drag a ship under. The giant squid was a legend, until 2012, when a team finally filmed one alive in its natural habitat. But why did it take so long? The giant squid lives at depths of 300 to 1,000 meters, a zone where pressure is still immense and light is scarce. Its huge eyes, the largest of any animal, help it spot predators in the gloom. Yet despite centuries of searching, it evaded cameras until recently. That first footage changed everything. It confirmed that the deep sea still holds creatures we barely understand. If a 13-meter-long predator can stay hidden for so long, what else might be waiting? The giant squid is a reminder that the ocean's depths are far from fully explored. So the legendary sea monster was real. But it's hardly the only surprise lurking in the abyss. In 2018, researchers in the Southern Ocean captured footage of a bizarre creature they nicknamed the headless chicken monster, a deep-sea swimming sea cucumber that drifts through the water like a ghostly alien. These discoveries keep coming. And in 2023, scientists filmed a fish at 878 meters, the deepest ever recorded. The Mariana snailfish thrives under pressures that would turn bone to dust. Its gelatinous body and high TMAO levels are nature's solution to the impossible. These discoveries are not anomalies, they are clues. Over 80% of the ocean remains unmapped and unexplored. Every dive into the abyss reveals species that challenge our understanding of what life can endure. But pressure isn't just a challenge, it also helps. At depth, the immense force actually aids some creatures. For example, deep-sea enzymes work faster under pressure, giving these animals a metabolic edge over surface dwellers. Evolution turns every obstacle into an advantage. The depth record holder isn't alone. Other snailfish species live at various depths, each with TMAO levels matching their habitat. This precise tuning shows how finely life adapts to pressure gradients, a molecular barometer for survival. Beyond molecules, some fish have evolved porous skeletons that compress rather than break. Their bones are filled with fluid-filled spaces, acting like natural shock absorbers. This structural adaptation reduces the risk of fracture under crushing loads, a lesson in engineering from nature. Cold is another killer. In polar deeps, water hovers just above freezing. Yet fish like the Antarctic toothfish produce anti-freeze glycoproteins that bind to ice crystals, preventing their blood from turning to slush. Without this, they'd freeze solid. Hydrothermal vents create underwater gardens. Giant tube worms, with their red plumes, sway in currents of superheated water. Their symbiotic bacteria turn toxic hydrogen sulfide into sugar. These oases support crabs, shrimp, and fish, all relying on chemistry, not sunlight. Bioluminescence isn't just for show. The deep-sea dragonfish emits red light, invisible to most prey, to hunt without warning. Others use counter-illumination, matching the dim light from above to hide their silhouette. It's an arms race of light and shadow in the abyss. In 2005, scientists found the Yeti crab near hydrothermal vents. Its furry claws are covered in bacteria it farms for food. This crustacean cultivates its own garden, waving arms in vent fluids to nourish its crop. A farmer in the abyss. The abyss teaches us that life is far more adaptable than we ever imagined. As oceanographer Robert Ballard put it, "We know more about the surface of Mars than we do about the deep ocean floor." And each new dive proves it. Life defies our expectations.